typical of me to set up everything and then forget to click start streaming. So everything is ready to go, except I didn't say go. So now we got it, yes. Okay, so let me get back to the school stuff. I actually double clicked on it. It's just that my computer is a little bit slow. Yeah, it's just an old computer, that's all. Hmm? Sorry? I don't have a whole lot of updates. At least I can still control when to update and when not to. So what you said about Microsoft, was that a new thing or has that always been the case? Mm-hmm. Okay, so if you I see. That doesn't seem very professional to me. And they can terminate my contract anytime. Yep, they can terminate mine. So, are there any questions about the Omega generator program? Yes.
So say that you supply like you have a case where you have more trials and outcomes. So like say you put like or without replacements. So say you put 3 to 0. So you have only 2 outcomes but 3 trials. What do you want us to do there? Because it's going to run out of.
Right. So you can just reject it.
Okay.
Just don't do a single thing. You
Okay.
can assume the input to be reasonable, which means if it is without replacement, the number of outcomes for the first trial is no less than the number of trials for the entire experiment.
Well, I was just wondering because how my algorithm did it is it would actually literally run out of outcomes,
Uh
so
huh.
it wouldn't print anything. It would just
Uh,
yeah.
okay. So it will only go as far as it can, but it
Mhm.
doesn't print anything.
Mhm.
Okay.
Yeah.
Yep. But that's okay too, because you can just kind of rule out that possibility. So, any other questions related to? Yep.
Do we have to make use of the RSV input from, or can we do like a user input just send?
You have to use the command line input, so you have to use ARGC and ARGV.
Okay.
If you're using code blocks, that's okay. Go ahead. Question? No. Okay. So for those of you who are using code blocks, do you guys know how to supply arguments to a program? Okay. Yes, under code blocks, okay, I can show you guys how to do it since some of you may be using code blocks to do it. Okay. Yes. Motherboards? I do not know of anything like that. Okay. That's okay. So if you're using code blocks and you want to use a project and you want to supply arguments to a program, you open the project first, okay? Because this won't work unless you have a project. So you go to project and then you go to set programs arguments, and this is where you can set the arguments. So in your case, it'll be the 3 numbers that you have to supply in the order that is specified in the homework assignment. So that means if you go back to your homework assignment, let me go back to the homework assignment first, which is the omega generator. Most of the other ones are kind of like that too. So the first argument is a base 10 number, that is the number of trials per experiment. Yep. Yes.
And are there any other ways to separate it, or just like
The separation of arguments is only white spaces or tab or
as much as you want, or like
yes.
okay.
Yeah, it should not make any distinction. So as long as there's at least one space between the arguments, it should be fine. But it does not use commas. Comma is not recognized as a separator from the command line perspective. Is that okay? Are we good? Okay. Any questions about the? Yeah, go ahead.
Okay, so besides like the general like requirements of the program and using the command line things, and it just sort of like can we implement it like however we want? So sort of
It has to conform to the rules that are outlined here. So basically, the output has to be lowercase, letters A to Z. Um, the order does not have to be exactly like this. So if you want to print, C, in this case, CB first and then CA, that's okay. The ordering is not important, but you have to output these lines, the way it is.
yeah, I was just we don't have to like use like the param structure you made or like
No, you do not. So the inside of the program, you can kind of choose how you want to do it, but the outside behavior of the program has to be as described in this case. So, any other questions? Any other questions regarding this particular program, which is due on Wednesday? No questions? Yep.
Because I missed your class instruction how to do this thing on.
Watch the video
Yeah,
again.
that was the question. Thank you.
Yes. Mm-hmm. Yep. So that would be the video before the break, the Wednesday before the break, I think. Yep. Any other questions? No other questions? All right. So this program is kind of interesting because it gives you an idea of how to generate all the elements in the set of omega, which is basically the set of all the possible outcomes. Now that is important because that's the denominator when you try to figure out what is the probability of something. Okay, so are there any questions about the omega, the terms of omega, and the terms of what is a trial, what is an outcome, what is an experiment, all those basic terms? No questions. All right. What about with or without replacement? Is that concept clear? Okay. So if those concepts are all clear, then we are going to move on. So we are going to move on to discrete probability. Um, and this is a new module. It's already open here. Yes?
did you show the how to put the arguments in code blocks yet?
Yes. So basically, it is just the three numbers. So in CoBlocks, you just this is for a different program, so that's why you don't want to do it like this. You just specify the three numbers like 1, 2, 3. Okay. Now obviously that doesn't make any sense. Okay. But the first one is the number of trials per experiment. The second one is the number of outcomes for the first trial, and then the last one is either 0 or non-zero. A 0 means it is without replacement. A 0 means it is with replacement. So you specify those three numbers, and once again, you can have like a 4, 2, and you can have as many spaces as you want before the next argument. The spaces are all going to be skipped. All right. So is that okay? Make sure that you click OK to accept it, before you run the program. Okay, and then try to use the debugger of CoBlocks as much as possible to make sure that the parameters are into that program first. Is that okay? Any questions about the homework assignment that's due on Wednesday? No questions? All right. So I'm going to close this one, just so that we don't have one more item to worry about. Okay, so module 0308 is about discrete probability. And in this particular case, we have all the usual stuff. Okay, so let's start from the beginning. So this one does talk about outcomes and events again. And once again, we talk about the birthday problem. The probability in this case is about the cardinality of the event that we're interested in. divided by the cardinality of omega, which is the set of all the possible outcomes for the entire experiment. So now the question is, what is E? What is the event that we are interested in? E can be anything that is a subset of omega. That's the bottom line. Okay, so the event, quote unquote event that we are interested in is by itself a set of outcomes, but these are the outcomes that we are interested in. So by dividing the cardinality of E by the cardinality of omega, now we know the probability of the events that we are interested in. So what kind of event are we talking about? In the case of lottery, okay, the event may be winning the jackpot. That's one event that you might be interested in. The second event is I'm getting something out of my ticket. May not be the jackpot, okay, maybe a few prizes down the line, but I'm getting something out of my ticket. That may be an event. You can also have the event being I'm not getting anything. I just spent a whole dollar and I'm not getting anything back. What is the probability of that? Okay, so your event is up to you to define what are you interested in, but omega, on the other hand, is not up to you to define. Omega is the set of all the possible outcomes. So are we clear on the concept of what is an event and what is omega? Now, because E is always a subset, can be a proper subset, can be the same as omega, what do you think is confining this ratio? In other words, if you look at this ratio, it has to be between which number and which number? 0 and 1, exactly. If it's a 0, that means it cannot happen, it's impossible. If it is 1, it means it is always going to happen. Is that okay? The birthday example is the other one. We talked about it, but this is the formalized discussion of that thing. So in that case, the event is either, okay, depends on how you look at it. So the event is either all the possible outcomes where the entire class has unique birthdays, or the complement of that, which means at least 2 people in class share the same birthday. So it depends on how you want to define the event. But omega, on the other hand, is all the possible outcomes. Okay, given about 40 people in a class, okay, let's say exactly 4 people in the class, what are all the possible ways to assign birthdays to each person in a class of 40? Is that okay? Are those concepts, clicking or not? Sort of, maybe. Examples. Okay, so the birthday example was already discussed before. Yeah. So let's move on and talk about this. So there are different ways to solve that problem. The birthday problem. This is one way. In the other class we use the other way. So let's try another one. Okay, let's try tossing coins. Okay. And at this time, we're going to assume the coin is fair. In other words, it is not loaded. So if a coin is not loaded, okay, if you flip the coin 5 times, what are the chances that you get 3 heads and 2 tails? I don't really care about the ordering, okay? I just count and go like, okay, 3 of the 5 trials ended up with heads, and the rest ended up with tails. So what is the probability of that? That is the question. Okay, so there are 2 ways to look at this. Okay, so we're going to do it the brute force way first. Okay, because the brute force way is usually easier to demonstrate, and at least we get the idea now of how to do it. Yep. Yes. So it definitely is related to that. So what I'm going to do is I'm going to use a spreadsheet to show you how to do it the brute force way, which is only good for illustration purposes. Okay, so when you're actually going to calculate probability, you want to use the closed form and not the brute force method. All right, so using the brute force method, I'm going to go to the cisp440 folder, go to shared, and I'm going to make an example here so that you guys can actually see it. So new spreadsheet. And then I'll rename it first just so that you guys can see it on your own device if you want to. So we'll rename it this one as coin toss example. Okay. All right. So the first thing I need to worry about is what is omega? What is my omega when we have experiments? Each experiment has 5 trials. Each trial is tossing the coin, and it is with replacement. Okay, because if your first toss ends on the head, can your second toss also land on the head? Yes. Okay, so that's why it is with replacement. Okay, so each trial does not affect the outcomes of the following trial. Is that okay? So how many elements do we have in this particular omega? The omega being all the possible experiment outcomes. How many outcomes are we talking about? 2 to the 5th, which is 32. Very good. Okay. So what I'm going to do, in the spreadsheet is I'm going to start with a 0. Okay. And you guys might have seen me done this already. And then the next row is just 1. And then we can replicate this one all the way down to row 32 or row 33 so that we have numbers from 0 all the way up to 31. This is a trick to get to each head and tail. So this is trial 0. This is trial 1, trial 2, trial 3, and trial 4. So there are 5 trials here. Each one is basically 1 digit of a 5-bit number. Because if you think about it, 0 is 0, 0, 0, 0, 0 as a binary number. 31 is 1, 1, 1, 1, 1 as a binary number. And everything in between is going to enumerate every possible ways to generate the heads and tails. You just have to think about, if the bit is a 0, it's a head or tail, and then the other one is the opposite. Okay, so I don't really have a preference of which way is which way. Do you guys want to have a particular way of saying, okay, 0 is head or tail? I think 0 being head is better because the 0 looks like a head and the 1 looks like a tail. Does it work? Okay, cool. All right, so the next task that we have is to convert the number n, which is just a decimal number, or it's just internally represented as an integer, into a binary number, either 0 or 1, because once I get a 0 or 1, I can generate the head and tail pretty easily. So how do we do that conversion? For those of you who are taking CISP 310, it's one of the questions that was asked before. Do you guys remember? You guys do not remember? Okay. So let's try this. So we know the overall operation is a mod operation. So what goes in between the mod operation? It's going to be an integer division. So that means we're taking the floor of a division. The division is going to be this n here divided by a 2 to the power of something. So whatever 2 to the power you want to divide it by, the power of 2, has to do with, are we talking about trial 0, 1, 2, 3, or 4? That determines which bit of a 5-bit number we are looking at. Are we looking at bit 0, bit 1, all the way up to bit 4? To get to this one quickly and easily, we can refer to the column of this particular cell, which is column itself. Okay, so now we can say to the power of column. But column starts with 1, which means this is already column 2. But so that's why I need to divide it by 2, so that it is 2 to the power of 0 with this one. Okay, and that ends the power, that ends the floor, and then mod the whole thing by 2, and that ends the mod. Yep. Say that one more time.
You said column -2.
Yes. Because column A it will return a value of 1, column B returns a value of 2. But I want my powers of 2 to start with power of 0, so that's why I have to offset it by 2. Is that okay? So I'm just going to work with some numbers here and make sure that we are getting alternating 0s and 1s. Cool. And are we getting 0? This is not working. It's not working because the reference to column A is lacking a dollar symbol, so that it is without the dollar symbol, it refers to the column to the left-hand side, and that's why it's not working. So with this, let's see, let's try it one more time. The next column should be 0011. Okay, and then the next one should be 00001111. Okay, so I'm pretty sure it's working now. Okay, but we want to look at these as heads and tails, not zeros and ones, right? So now we can do a conditional statement. So we can say if this is non-zero, then we say is a head. Let's see, if it's non-zero, it is a tail. And if it is a zero, it is a head, okay, because of the shape of the digit. So we have a head here, and then we can go all the way to the end, and then just replicate everything down here. Okay, so let's double check and make sure that this it's almost like a truth table, except it's labeled not as true false. So does it look right to you? Okay, the first column is alternating. The second column is head, head, tail, tail. The third column is head, 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 tail, 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 tail. The fourth column is this, and then the last column has one half, the entire block being heads, and then the other half, entire block being tails. So I think that works. Okay, I'm fairly convinced that this is working. So this is how I can quickly, well, okay, sort of quickly, generate all the possible outcomes for an experiment that has 5 trials. Each trial is tossing a coin, and I only want to know whether it's a head or the tail. Is that okay? All right. So the next column is going to say, should we count it? Is it part of the event that we want to look into? In other words, remember we want 3 heads and 2 tails, right? That's what the question was asking, okay? So we can do it kind of like this, okay? So we can say number of heads, okay? And there's a really cool function called countif. So countif allows you to select a range of values, and then you can specify the criterion, which means in this case it is just heads. Okay, so there are 5 heads in this one, and if I scroll all the way through like this, that gives me the counts of number of heads for each trial. Each row represents one experiment, and then column G is summarizing the entire experiment and ask, okay, how many heads do we have in this particular experiment outcome? Is that working? Okay, so we'll just kind of randomly pick one and check. Okay, row 12. Row 12, has head, tail, head, and there are 3 heads. Okay, seems to be working. Questions? Yes?
No.
Oh, okay. Oh, okay. All right. So now we have to. Okay, come on. Okay, there we go. Okay, I'm just trying to shrink the column a little bit. And what are we interested in again? 3 heads, right? Everything that has exactly 3 heads. So we're going to use countif again, but this time as a summary. So this time we say countif, and then the range is going to be all the way from here, all the way down to this cell over here. And then what we're looking for, now this time I'm not really sure whether we can specify that. We can say equals to 3, okay? And we'll see if it works. Looks like it works. Does anyone want to do some actual counting?
You can just quickly count.
You can quickly count. Okay, so we got 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10. So unless I made a mistake, counting, it seems to be correct. So are we doing okay so far? So what is the probability? We went through the whole table, right? We enumerate all the possible experiment outcomes. We did some counting, and then we did a summary. But what is the probability? What is the probability of having 3 heads out of 5 coin tosses? 10 over 32, exactly. It is the cardinality of the event. In this case, anything that can give me exactly 3 heads, order is not important, divided by the cardinality of omega, which is 32 in this case. Yes?
So, wasn't it supposed to be 5 trials, not 4 trials?
5 trials. There are 5 trials. Trial 0 to trial 4.
Oh.
Yep. Counting from 0. Yep. Any questions about this spreadsheet other than the commands and stuff like that in Google Sheets? Yep.
What would be the easy way to find the cardinality of this E without this spreadsheet?
Aha! I like that question. Let me repeat that question. So the question is, can we figure out the cardinality of the event without using a spreadsheet? In other words, if I say, let's consider 128 coin tosses, and I want to find out exactly the probability of having 61 heads, okay? You don't want to generate a table because that table is going to have 2 to the power of 128 entries, which is going to be a pretty big number, right? And then you have to do all the counting. I'm pretty sure Google Sheets is going to be running out of resources if you were to do it this way. But there's a mathematical way to do it. Okay, so there's a mathematical way to find out the cardinality of E in this case. And it has to do with combinations and permutations and all that stuff. So we're going to move on and talk about that. I like that question. But we are going to answer that question as we read on. There will be the answer, just a little bit later. So the answer has to do with, this is combination. It is also known as 3 choose 3, or you can say C and then 5, 3 as parameters, or in the spreadsheet it's called combin, C-O-M-B-I-N, 5, 3. Okay, it's the combination, it's the number of combinations of 5 choosing 3. Ordering is not important. Okay, so how do we get to this one? Why is it not important? So what you want to do is to look at something like this, and instead of looking at this as head, head, tail, tail, head, where ordering certainly is important, but you want to look at the index, the positioning of the head versus the tail. In other words, when you look at this one, you say this one is 0, 1, 4. Okay? 0, 1, 4, but look at it as a set of 0, 1, and 4. So my question really is asking, if I start with a set of 0, 1, 2, 3, 4, how many ways can I pick 3 out of the 5 things in this set? That would answer exactly the same question of how many ways can I end up with 3 heads out of 5 coin tosses. Let's think about this, okay? Because I just said something that doesn't seem to have any connections, okay? If you establish that connection right away, good for you, okay? But it may not make a connection right away. So let me say that one more time. Okay, and I'm going to use mouse pad here to illustrate that idea. Okay, so choosing the number of ways, okay? Number of ways to choose 3 elements out of 0, 1, 2, 3, 4 is the same number to have 3 heads out of 5 coin tosses. That's what I'm claiming. Why is that the case? Because I'm representing head, 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 tail, tail as 0, 1, 2. I'm remembering the index of the positioning of the coin toss, the trial itself, that has a head. That is another way to encode the result of each experiment. Is that making any sense? So that means an empty, if I choose nothing out of the 0, 1, 2, 3, 4, that means I have no head in that particular trial or experiment. Is that okay? If I have 0, 1, 2, 3, 4 itself as the set, that means everything is a head. Every single trial of the experiment is a head. Yep.
Could you ask, how many proper subsets that have 3 elements of the main subset of the main set?
How many subsets, not proper subset, because we don't care about whether it's proper or not. How many subsets can I basically create by choosing 3 out of the 5 things in the original set, which is 0, 1, 2, 3, 4. So is that is that working? Why it is 3, 5 choose 3? Because the way you choose something out of a set is order independent. Ordering does not play a role of whether you have a set that is known as 0, 1, 2, 2, 1, 0, 2, 0, 1, and so on. It doesn't make any difference. Are we doing okay? So is that answering your question? So that means we can end up with a general equation. So we keep going like this. We have a general equation. Let me see, where did I put it? Okay, I didn't put it here. So there's no general equation here, but to answer your question, the general equation is like this. So let me go back to the, so given n tosses in an experiment, we want m of those as heads. Okay, the probability of that happening is basically the number of combinations of n choose m, and then the whole thing divided by 2 to the power of n in this case. So that's basically the closed form to answer your question. But before we take this one and go like, yep, okay, that sounds like it makes sense, and let's just move on. Let's test it, right? Because in our discussion here, n is 5, m is 3, so we can actually check this out. See if it gives us the same kind of numbers. So we go to the spreadsheet again. So let's go back to the spreadsheet. And this time I will do one calculation based on this 10, which is counted by the number of outcomes in experiments, okay, which is 32. We'll come up with this number. But then I will also use that equation that I talked about earlier, which is the number of combinations of 5 choose 3 divided by 2 to the power of 5. And, oops, I made a mistake because it is supposed to be a comma separating the two values in a function call, and they turn out to be exactly the same. So this gives me a warm and fuzzy feeling that that equation is not totally wrong. Because it takes one counterexample to show something's wrong. This is a validation that, at least in this case, it is not wrong. So are we still doing okay so far? So that was a good question, because we wouldn't want to have to do something like this to figure out the probabilities all the time. So switching back to the notes, there's one more thing that is kind of interesting. What if the coin is not fair? What if it is loaded? Okay, so if it is loaded, then we can no longer assume that it's 0.5 and 0.5 anymore. So if it is loaded, then we will use P as a symbol to represent what are the chances of landing on the head. Then the chances of landing on the tail is going to be Q, which is basically just 1 minus P. Does that make sense? Okay, because if it's not landing on the head, it has to be landing on the tail. So if the chances of landing on the head is P, then the chances of landing on the tail is going to be 1 minus P, which I call Q, just because it makes the following discussion a little bit easier to do. Okay, so what we end up with here is this is the actual total probability of landing in any possible way. Okay, which kind of makes sense. And then you look at this and go like, that is useless. It's totally useless because P is some kind of probability. Q is 1 minus P. So that means P plus Q has to be 1. 1 to whatever power is always 1. Why do we want to come up with this kind of complicated, convoluted way of looking at 1? Well, let's check out this thing here, okay? Now, I'm hoping you guys still remember binomial equations and stuff, right? Yes? Okay. So if you multiply, if you forget the fact that P plus Q is 1, okay, you just look at P as one variable, you look at Q as an independent variable. If I ask you what is P plus Q, the whole thing to the power of 5, can you figure out all the terms? Please say yes. Yes. Okay, good. I think I heard that. Okay. So now the question is, we know each term is going to look like this. Okay, each term is going to be p to the power of something times q to the power of 5 minus that something. Makes sense, right? So the power that the power of p and the power of q should add up to 5. But then you also have a multiplier of ki, okay, because we know that p to the power of 5, q to the power of 0, there's only one of those. P to the power of 0, q to the power of 5, there's also one of those. But what about the stuff that is in between? Okay, but I'm just going to call it ki, okay, just so that we can defer that discussion. Okay, we just call it ki. But when you add up the sum, that's what the sigma is. So that's why index I goes from 0 to 5. And then I'm just using I as an index to control which constant k we're talking about. What is the power that p is raised to, and what is the power that q is raised to, which is just 5 minus I. Is that okay so far? Okay, so the next task is, so how do we figure out those constants from k0 to k5 in this case? Well, I mentioned binomial a little bit earlier, right? So that's why we have. What does Pascal have anything to do with that? I mean, you guys were reading ahead a little bit here. 4.1 is Pascal's identity. What is Pascal's identity? The one thing that you guys already know about Pascal is Pascal's triangle, right? But Pascal's triangle is a result of Pascal's identity. So let's check out Pascal's identity first. Pascal's identity. Okay, come on, scroll. There we go. That's a good one. Did you just come up with that?
Yep.
Pretty good. Okay, so Pascal's identity is n choose k plus n choose k minus 1 equals to n plus 1 choose k. That is Pascal's identity. Then you guys will ask, then what is all that stuff in between? I mean, we got 10 rows here. What is all that stuff in between? That's the proof of Pascal's identity, or one of the proofs of Pascal's identity. Let's check it out, okay? Let's make sure that this makes sense, okay? Because in this class, it is discrete structure, also known as discrete math. So the math component is important in this class. So I'm going to zoom in just a little bit so that we can go from one row to another row and just go focus on the first one at this point. So we'll focus on the first row. What did I do? What did I do to go from the left-hand side, which is a very nice, good-looking thing, to something that looks kind of messy? That's the definition of combination. Okay, so n choose k is by definition n factorial divided by k factorial times n minus k the whole thing factorial. Okay, the other one looks a little bit uglier because it is n choose k minus 1, and that's why we have some k minus 1 terms here. Going from the first row to the second row, what did I do? Nope, there's no distribution. I just use a rule of association. I changed the order a little bit. So instead of n minus k minus 1 as a whole thing, I group n minus k as one whole thing, and then plus 1 because it's a negation and a negation, so that's why it's a plus 1. Is that okay? From the second row to the third row, okay, what did I do in that case? That looks kind of... I multiply the numerator by k. I multiply the denominator also by k. Now this one is obvious, okay, because it was n factorial. If I multiply n factorial by k, obviously it becomes n factorial times k. What about the denominator? That
K factorial is actually k times k minus 1 factorial.
exactly. Good job. Yep, exactly. So that's how I go from k minus 1 factorial to become k factorial, because k minus 1 factorial times k is k factorial. Okay? All right, so let's move on from here to here, from the third to the fourth. What did I do in that case? I divide both the numerator and the denominator by n minus k, the whole thing plus 1. Okay? So the numerator is pretty clear, okay? But the denominator is kind of clear too because we just lost the last term of that factorial. So it's simplified from n minus k plus 1 factorial to n minus k factorial. Is that okay? So I know this is not your usual algebra because factorial has its own kind of special tricks that you can do, but it is still kind of algebra. And from fourth to fifth, what did I do? Looks kind of nasty. What I did from here to here is on the left-hand side of the multiplication. So what did I do to these two terms? I didn't do much. The numerator is just multiplied by 1. But I didn't say it as 1. I say it as n minus k plus 1. So I multiply it by n minus k plus 1 divided by n minus k plus 1, which is just 1. And then what did I do? Ooh, but when I do that, I can now, you can see how the two terms have exactly the same denominator. So I can combine the denominator. But when you look at the numerator, they look like the numerators themselves also have the same denominator. Whew. Okay, is that making any sense? Okay, so I can combine those. So now we can combine those, and because I'm dividing by this and then dividing it by that, so I can divide it by the product of those two, right? Is that making any sense? I'm basically moving this into the denominator, which is okay. Okay, so the denominator becomes a product of these two terms, and then what is left here is, I did one thing here, which is distribution. I distributed this minus k times n factorial out of this whole term, so it can be canceled out by the other n times n factorial times k. Is that all right? Okay. So when this is all done, I end up with n plus 1 factorial divided by k factorial times n minus k plus 1 factorial. But that doesn't look like what we are looking for, so that's why I have to regroup things a little bit. And I say n minus k plus 1 is really the same thing as adding 1 to n first, and then subtract k from the sum. So now it becomes clear that we have n plus 1 itself as a term, k itself as a term, and then we have basically n plus 1 as a term divided by k factorial times n plus 1 as a term minus k, the whole thing factorial, which then fits into the format of combination again. And that's how we ended up with n plus 1 divided by k. Is that okay? How is this giving you Pascal's triangle? How do you look at this and see a triangle? Let me zoom out again, just to make sure that we are missing something. How does that look like a triangle? It does not. Huh? Oh, I see. How it's wide and narrow. Okay. It's an upside down triangle, yes. But it defines the terms of Pascal's triangle. Okay? So what you need to do is to think of n as rows in a triangle, and then think of k as how many terms from the left-hand side of that row of a triangle. Yep.
You expect us to do proofs like this to give us different ends or whatever?
I would expect you guys to be able to reapply some of the techniques in this proof, yes. I cannot say how to practice this stuff, but so basically what you need to do is to figure out how I went from one step to the next, what kind of trick did I use, and there are only so many tricks you can do with factorial. So how did I cancel out terms? How did I come up with the same denominator? That is the kind of thing that you have to, I don't know, I guess you have to add it to your repertoire of your proof techniques. Okay. Okay, so getting back to this one, how does this look like Pascal's triangle? Once again, and yeah, go ahead. A G function? No, not quite, not quite. But okay, so let's check out this one here. Okay, so let's do it like this. When n equals to 0, okay. So when n equals to 0, what can k possibly be? I have nothing, and I can how many things can I choose from nothing? Nothing, 0. Okay, so that means k can only be 0 in this case. And how many ways can I choose nothing out of nothing? Okay, one way. Okay. Then the next row says n equals to 1. I got one thing now. Now the question is, how many ways can I choose nothing out of one thing? There's always only one way to choose nothing out of anything. Then the next question is k equals 1. How can I choose one thing out of one thing? There's only one way to choose one thing out of one thing, right? Seems to make sense to me. N equals 2. I got two things now. How many ways can I choose nothing out of two things? One way. How many ways can I choose one thing out of two things? I got A, B, right? So how many ways can I choose one thing out of A, B? Two ways, okay? I can choose A or B, right? So we got two ways. And how many ways can I choose both things out of the two things that I have? Only one, A, B, right? Okay, cool. N equals 3. I got three things now. I got one way to choose nothing out of three things. How many ways can I choose one thing out of three things? Let's see whether it makes sense, right? I got A, B, and C. I only want one out of A, B, and C. How many ways can I choose one thing? Three ways. Okay, cool. How many ways can I choose two things out of three things? In other words, how many ways can I choose the one thing to miss out of the three things, right? So it's the same question as the previous one, except we look at it from the flip side. Three ways again, because I can miss A, I can miss B, or I can miss C. So three ways, and then how many ways can I choose three things out of three things? A, B, C, just one way. Do you see how this relates to Pascal's triangle now? Yep. But do you also see how, okay, let's work with n equals 4, because then it becomes really obvious. Okay, we got one here. How do you know this is 4? Did you know this is 4 because you think about how many ways we can choose one thing out of 4? Or did you apply the Pascal's identity and go like, oh, we just had to add up the two things on top to become this one? That's Pascal's triangle right there. 3 plus 3 is 6. 3 plus 1 is 4. And then the last one is always a 0, which always bothers some people. It's like, oh, then we have some exceptions, right? The first one and the last one, they're kind of exceptions. It is not the sum of the item on top and the item to the top and the left. I got one easy solution for those people who are always asking, I don't like exceptions. I want to use the same rule to calculate everything. Let me answer your question.
I was gonna ask that too. That's kind of bad.
This isn't, okay, so Pascal's triangle is living in an ocean. This is an island in an ocean. The ocean is made out of zeros. So you just basically say, okay, we'll put zeros here and put zeros here. Okay. So now your rule works, right? Everything is just the thing on top plus the thing on top and to the left. Then you're drowning. You don't want to get out of the island. You only want to step at the edge of the island and go like, I'm just going to reclaim one more row of this island. You don't want to step into the ocean. Yeah. Then yep. Is that making any sense? So is that making all of you, those of you who are completely rule-based and go like, yes, I'm happy now because we don't have exceptions now. Cool.
I don't mind exceptions. I just need to know when to consistently use them.
Then you like our tax form
Man, I don't know, man.
then.
I guess so, man.
I cannot imagine too many countries that actually require the use of a software to report taxes. In most countries, they just give you the money after taxation, and then when you buy stuff, you pay tax, at the time, depending on what you're buying. So at the end of the year, there's no actual form to fill in. There's no actual calculation. You just basically say, "Yep, I pay this much tax," and send it in.
There's a whole industry based around accounting in America.
Yeah, well, we have.
Business
Whole
system.
industry. I thought it was
Yeah.
just separate contracts.
There have been bills in the past to try to make our tax system where you don't have to fill out forms like that, where it's just they give you a set amount of money, they charge you in your bank account, but it's always shot down by lobbyists.
Oh damn. Oh okay.
Yep. Well, I'm missing an open paren here, but you guys probably know which paren we are talking about. Oh, what is that back quote doing here? Okay. So basically, this answers the question. Okay. If n is a natural number, p plus q to the power of n. Oh, actually, it's not missing. That's the pair of parentheses here. So p plus q, the whole thing to the power of n, can now be expressed as a summation of individual terms. Each term is p to the power of I, q to the power of n minus I, and I is going from 0 to n. But the number of those things that you have, guess what? It's based on Pascal's triangle, which is n choose I. So are we still doing okay so far, connecting everything from the initial example of 5 coin tosses, and we want 3 heads out of 5, all the way to here? Remember, what is P? P is the chances of landing on the head. Q is the chances of landing on the tail, right? So this gives us a equation of figuring out, even if the coin is loaded, I can still calculate what is the probability of landing like 3 times on the head out of 5 times, when the probability of landing on the head is actually tilted to, let's say, 0.3. I can still figure out that probability. Is that okay? Not the loading the coin part, but the understanding of that. Is that okay? Cool. Well, let's see, whether we can use a spreadsheet to do some illustration of this concept. Okay. So what we'll do is, let's go ahead and start a new sheet here. Okay. So basically, what we're doing is we are looking at P, which is the chances of landing on a, landing on a head. Okay. So when it's 0.5, and then this time we want to look at the probability of 3 out of 5 coin tosses is a head. Okay. So we already know it's based on the combination 5, 3, and it is to the power of, oh, I forgot the equal sign here. There we go. Times, okay, I don't like the help here, plus this to the power of 3 times 5 minus 3, plus the power of 1 minus this number, to the power of 5 minus 3. There we go. Same number that we got. Okay, I strung the column a little bit too much. That's why we lost the 5. So now the question is, what if it is 0.4? Okay, what if it's 0.3? Okay, let's see if the spreadsheet is smart enough to figure out the step of this copy. Yep, it does. We can go down to 0. And in other words, the probability of landing somehow, having 3 coin tosses out of 5 landing on the head, when the chances of landing on the head individually is only 0.1, the chances of landing it on the head 3 times out of 5 is a very, very small chance. It is less than 1% of a chance. So is that okay? Cool. All right. So getting back to the notes, there's another proof, okay? This is another proof which is called the binomial theorem. So what is the binomial theorem? The binomial theorem is this thing here. This is the binomial theorem. They go like, okay. So in other words, what we really want to prove is p plus q to the power of n is the summation of I equals to 0 to n. And then each term is n choose I times p to the power of I times q to the power of n minus I. So how do we prove that? So this is the time that I think it may be the first time. No, it's not the first time, but this is kind of like maybe the second time or the third time that we talk about proof by induction. Okay, remember proof by induction? It also involves an island and a cruise ship and turtles in between.
Turtles, I love turtles. Not as turtle soup.
Do you guys remember that? Sort of? No? Okay. All right, so proof by induction goes like this. Okay, let me get rid of that. So we are talking about proof by induction. Proof by induction has two distinct steps. The first step is called the base case. Are you guys not remembering this at all? Okay. So in proof by induction, you have to basically prove that some kind of theorem, okay, I'm going to use T, uppercase T as a theorem, and it has to be, huh?
Oh, so was this the time when you told me that when the guy did his whole research and you did the proof and he wasted his 4 years of doing something?
That is when I talked about, how you have to prove a theorem before you accept it as truth. Okay? So prove a theorem, okay? So the theorem is going to be in the form of for all I in a particular set, okay? The set needs to have a beginning of some sort, okay? So I'm going to have a beginning here, we'll just call it, b here. But it doesn't need an end. So it can be b plus 1, b plus 2, b plus 3, all the way up, okay? And we want to prove that T of I is true, okay? So the theorem itself is broken up into tiny pieces. Each piece is basically just saying T of something is true. T can be some kind of long, huge expression. We don't know what it is, but it's parameterized by I. I has to, so it has to be true from the range of B all the way up to some end, okay? And the end doesn't have to be definite, can be infinite. And B can be 0, okay? Can be 1, can be some fixed number. So the base case is to say that prove that the theorem is true for the case when I equals B. In other words, prove that T of B is true. That is your base case. Okay, so the base case says, okay, I'm not going to look at every single thing in this entire set. I'm just going to look at the first thing, okay, which I look at here as B and go like, can I prove that T of B is true? That usually is easy because you're focusing on one single constant and it is concrete. So you can just go through algebra and say that, yep, that value is the same thing as that value. Done. So the base case typically is easy. Then you have the induction step. This is where you step on the back of turtles. You guys are not remembering? Or did I? Okay. Some of you remember, some of you do not. Okay. Okay, so in the induction step, okay, we use an assumption. We say assume, okay? Assume T of some K is true. Now, this is important, okay? We assume it's T of some K is true, and K is not actually defined. We don't say K is 5, we don't say K is 20, or K is 200. We just say that for some K, T of K is true. That's all we're assuming. But if you can make that assumption, prove that T of k plus 1 is also true. That's your induction step. So the induction step starts with an assumption and say that let's assume the theorem is true when I equals k. Now can I prove that the theorem is also true for the case of I equals k plus 1? That's the induction step. If you can make that proof, making use of this assumption, then you have completed proof by induction. Is that okay? Okay, so for those of you who forgot about the island, cruise ship, and sea turtles, I'm going to redo that one a little bit, okay? So the theorem is tech can walk all the way from the island to a cruise ship. Okay? The base case is tech is standing on the island right now. The induction step is saying, assuming tech is standing on something and he's not drowning, okay? There's always a next step that he can take. Okay? And the sea turtles are the ones that are making my steps from the island to the cruise ship. So if I can show you that no matter where I stand, there's always a sea turtle that is within 1 footstep away from me to the direction of going to the cruise ship, then I have just proved the theorem that I can eventually get to the cruise ship. Is that making any sense? Okay? So that's the essence of proof by induction. In other words, the induction step is just saying that I'm standing on something. It can be the island, which is the base case. It can be the back of a turtle already. I just need to know whether I can be assured that there's a sea turtle that is 1 step ahead of me. That is all I need to do.
Now the goal is just to prove that there is a sea turtle.
Yep. So I need to make sure that my sea turtle bait works correctly, and there is at least enough sea turtles to get this done. I need 2 sea turtles, right? Because the moment I step onto the next sea turtle, then the sea turtle that was behind me can now swim ahead of me. So 2 sea turtles can get me all the way to the cruise ship. Yep. Now, of course, some of you who like to water ski will just say that, but with two sea turtles, you can just do it this way. But that wouldn't be proved by contradiction. That would not be proved by induction, for one thing, and that would also be not a discrete math problem, because what makes proof by induction discrete is step by step. Prove it for I equals k. The next one is I equals k plus 1, which is discrete. If you step on both sea turtles and they're just swimming in the direction of the cruise ship, that's calculus. That's continuous math. Okay? Which then you can also calculate the wave function, how fast you're going, how slow you're going, that sort of thing. Okay, so given that this is the structure of proof by induction, which is very, very important, okay, how are we going to prove it? So the base case is basically to say if when n equals to 1 end of the entire range of values, since uppercase N is the set of all natural numbers, can someone name a particular good starting values that I can use? Does natural number start with a particular value? Is there a smallest of all the natural numbers? 0, right? Okay, so we just say, okay, what if n equals to 0? Can we prove that when n equals to 0, p plus q to the power of 0 equals to I equals from 0 to 0, 0 choose 0, p to the power of 0 times q to the power of 0. No, p to the power of 0 times q to the power of I, n. 0. Because n is 0, I is 0, so it's 0. Does that make sense? Everything is 0. So So that it makes sense. P plus Q to the power of 0 is 1. We know that. 1 can also be re-expressed as P to the power of 0 times Q to the power of 0. But then we can also throw in another 1 here, which is 0 choose 0. Okay? Then the whole thing makes sense. Is that okay? That's your base case. So this is why I said the base case is easy to prove, because you just plug in 0 into n, you figure out what is the left-hand side, you plug in n equal to 0 to the right-hand side, you figure out what the value is, and you just ask a question. Are these two values the same? If they are the same, you're done with the base step of proof by induction. Is that okay? So now what about the induction step? Okay, we got 5 minutes left. I think that's enough time. So the induction step says, okay, let's make an assumption that we have done this several times, and we can prove the theorem up to n equals k. So in our case, it means we assume that we have already proven that p plus q to the power of k equals to the summation of I equals 0 to k choose I times p to the power of I times q to the power of k minus I. That's an assumption, but that's what we start with proof by induction in the induction step. So now the question is, okay, if I want to prove n equals to k plus 1, can I start with this and end with this? That is the question. All the steps in between is a part of the proof. But that's where you start. Okay, this is where you start. This is where you want to end up with. And one of the steps probably has to involve the assumption. So can someone point out where I use the assumption? Yep. The second line uses the assumption right away, because I break up p plus q to the power of k plus 1 into p plus q by itself times p plus q to the power of k. And then I right away made use of the assumption and go like, but we know what that looks like. Okay, expand it to a summation term. The rest is just playing with summations and stuff like that, moving terms around a little bit, and then we end up with that. Yep. Details. Well, we got time to look at the details. We got 2 minutes. So let's take a look at the details here. What did I do to go from here to here? From here to here. Yep, exactly. So p plus q does not depend on k. I just multiply it to the terms inside the summation itself. What about from here to here? What did I do? I break it up into 2 because I distributed the p plus q so that p goes with one side, q goes with the other side. Is that okay? So if this side has p to the power of I to begin with, now it becomes I plus 1 because I got one more p term to that side. This term goes to the cube side, so now it has a plus 1 compared to before. Okay. Going from here to here, what did I do? I break off some terms, didn't I? So what you need to do is to look at the indexing of the summation of the sigma. It went from 0 to k earlier. Now it went from 0 to k minus 1. What happened to the term that got broken off? It became its own term outside. And I can do the same thing with the other one. It went from 0 to k before. Now it went from 1 to k. And inside it's the same. Okay. So all I did is to pick out the term when I equals to 0 and separate it into its own term. And then from here to here, between these two steps, what did I do? I think I just moved things around. Oh, I reindexed it. Yep, you're correct. I reindexed. So this one went from 0 to k minus 1. This one went from 1 to k. But I have to change the term inside to kind of adjust for that. So what used to be I is now I minus 1, so that I keep the same number, same value. So what used to be I is now I minus 1, but since I did not want to write I minus 1 in parentheses, I just do a plus 1 here. But that did not really change the value of the sigma. It just changed the indexing terms. On the other side, I haven't done anything yet, okay? What did I do from here to here? I combine the sigma because now they have the same index. So that means that I can take this term, I can take this term, put those together because they can share the same index. And what did I do from here to here? I applied Pascal's identity. Very good. So I look at this thing here, and then I look at this term. Hey, looks like something that we have seen before, even though the variable names have changed. So that is Pascal's identity. So this itself is why we talked about Pascal's identity, is so that we can use it as one step of the proof of the binomial theorem. And then how did I go from here to here? Yep, I put these two terms back into the sigma. And that's it. Is that okay? So the technique that I used, you can just kind of, I know we are running out of time. So when you go through these notes again, you might want to write down next to it what technique I used in each step. Okay, because that's basically how you can learn about the steps of proving and the special techniques they can use when you're dealing with sigma. All right. So on Wednesday, we're going to go through one of the practice exams, and then next Wednesday, we're going to have the second exam of this class. All right. And Wednesday is also when the homework assignment is due, so you have some work ahead of you.